What NASA just discovered about our solar system. Somewhere in a clean room in Houston right now, scientists in white bunny suits are handling grains of rock older than Earth itself, picking them apart flake by flake with tools designed not to breathe on them wrong. A few 100 million miles away, a spacecraft the size of a small car is threading Jupiter's radiation belts just to skim past an ice-crusted moon for a matter of minutes. Out past Neptune's old orbit, moving faster than a bullet and farther from home than anything we've ever built, a 49-year-old machine is still phoning in data from a region of space with no official map. Closer to the sun than any human-made object has ever dared go, a probe about the size of a golf cart just became, officially, the fastest thing our species has ever constructed. And on the floor of a dead volcanic plain on Mars, a lander that stopped moving years ago spent its last months listening, actually listening, with a seismometer sensitive enough to hear a pin drop from across a continent, to the sound of the planet's own heartbeat. None of this is science fiction. It is NASA's actual, published, peer-reviewed body of work from roughly the last 5 years, stitched together from more than half a dozen missions that have almost nothing in common, except the fact that they're all still running, all still sending data home, and all still forcing scientists to revise what they thought they understood. If you haven't been keeping up, the picture of our solar system that's emerging from all of this is stranger, wetter, hotter, and more chemically alive than the tidy diagram most of us grew up memorizing in school. This isn't a single headline from this morning. It's a body of results that's been accumulating for years, built flyby by flyby, sample by sample, seismic wave by seismic wave, and taken together it adds up to something bigger than any one discovery could say on its own. Over the next couple of hours, we're going to walk through that body of work properly, not as a list of trivia, but as a set of stories, each with its own history, its own hardware, its own scientists who had a hypothesis going in and got something else coming out. We'll spend time with the asteroid that turned out to be a fossil of a wetter solar system. We'll go inside the ocean moon that may be venting its own chemistry into space where we can taste it. We'll ride along on a spacecraft built to survive temperatures that would vaporize almost anything else humans have ever flown. We'll listen to a planet's interior through a seismometer sitting motionless in the Martian dust. And we'll follow 2 probes older than most of the people watching this, still working, still transmitting, from a region of space where the rules our textbooks describe may simply not apply anymore. Along the way, I want to be honest with you about something that gets lost in a lot of space coverage. Real scientists are careful. When you hear a phrase like consistent with or suggests but does not confirm, that's not evasive language. That's what it sounds like when people are doing their job correctly. Nobody in this program is claiming we found life, or solved the sun, or finished mapping the outer planets. What they're claiming and what they can back up with data is that the solar system keeps turning out to be more interesting than the models predicted, one mission at a time. That distinction between we found something extraordinary and we found something we can prove is going to matter throughout everything that follows. So let's start where a lot of this really began, with a spacecraft that flew out to a small, unremarkable-looking rock, touched it for about 6 seconds, and came home with something nobody quite expected. Part 1. The rock that remembers water. To understand why Bennu matters, you have to go back further than the sample return. You have to go back to 2016 when NASA launched a spacecraft called OSIRIS-REx, an acronym that, unpacked, tells you almost the entire mission plan: origins, spectral interpretation, resource identification, security, regolith explorer. Every one of those words was a design requirement. This wasn't a flashy mission built to grab headlines. It was an engineering-heavy sample return effort aimed at a very specific kind of target, a carbon-rich, or carbonaceous, near-Earth asteroid old enough and undisturbed enough that its material might still preserve chemistry from the very earliest days of the solar system, before planets had finished forming, before Earth had an atmosphere or oceans of its own. The target they picked was Bennu, a rubble pile asteroid a little under 500 meters across, roughly the height of the Empire State Building, if you tipped that building on its side and let it tumble slowly through space. Bennu isn't a single solid rock. It's a loosely bound pile of boulders and gravel held together mostly by its own weak gravity, the debris left over from a larger parent body that was shattered in a collision sometime in the deep past, likely well over 1 billion years ago. That rubble pile structure matters, because it means Bennu behaves less like a rock and more like a loosely packed pile of gravel in microgravity, a detail that very nearly wrecked the entire mission before it started. OSIRIS-REx reached Bennu in December 2018, and almost immediately the mission team had a problem. Based on Earth-based telescope observations, they had expected a relatively smooth surface with open areas suitable for a sample collection maneuver. Instead, close-up imaging revealed a surface covered in boulders, some of them large enough to seriously damage the spacecraft, with almost no flat, clear ground anywhere. The team had to spend an additional 2 years mapping the asteroid in exhaustive detail, identifying a site barely larger than a few parking spaces, nicknamed Nightingale, that was judged survivable. That delay wasn't a failure. It was exactly the kind of course correction real space missions require when reality doesn't match the model. And it's worth mentioning because it's the same story you'll hear again and again throughout this program. Expectation meets data, and the mission adapts. The sample collection maneuver itself, executed in October 2020, was almost absurdly delicate for something happening 200 million miles from Earth with a radio delay of several minutes each way, meaning no human could steer it in real time. The spacecraft carried an articulated arm called TAGSAM, the touch-and-go sample acquisition mechanism, tipped with a collection head about the size of a dinner plate. OSIRIS-REx descended toward Nightingale, made contact with Bennu's surface for approximately 6 seconds, and fired a burst of pressurized nitrogen gas into the regolith to stir up loose material, which the collection head then caught as it lifted away. The contact was so brief, and Bennu's surface so loosely packed, that the spacecraft's sampling head actually sank several centimeters into the asteroid, like landing on a ball pit rather than solid ground, a discovery that reshaped how scientists think about rubble pile asteroids generally. The maneuver worked so well that it collected far more material than the mission required, so much that some of it began leaking out around a mylar flap that hadn't fully sealed, forcing the team to stow the sample earlier than planned to avoid losing any more of it. Then came the long trip home. OSIRIS-REx didn't return to Earth immediately. It couldn't, given its trajectory and fuel budget. So the sample capsule spent nearly 3 years in transit before being released to fall through Earth's atmosphere and parachute into the Utah desert in September 2023, while the main spacecraft itself, still healthy, was retargeted for an extended mission to a different asteroid, Apophis, arriving around the time of that asteroid's unusually close 2029 Earth flyby. That extended mission now flies under a new name, OSIRIS-APEX, the same spacecraft, repurposed rather than replaced, with its sample collection hardware no longer needed but its cameras, spectrometers, and laser altimeter all still fully functional. The target is genuinely unusual in its own right. Apophis, a roughly 340-meter asteroid that will pass within about 20,000 miles of Earth's surface on April 13, 2029, closer than the ring of geostationary communications satellites, and close enough to be visible to the naked eye across parts of the eastern hemisphere without any telescope at all. That kind of close planetary approach doesn't just make for a striking sky event. Scientists expect Earth's gravity to measurably flex and reshape Apophis's surface during the flyby, potentially triggering landslides or shifting loose material, the way tidal forces do to Earth's own oceans, but acting instead on a loosely bound pile of rock. OSIRIS-REx is planned to arrive shortly after that encounter, specifically to document whatever changes the flyby leaves behind, using the same spacecraft that already proved at Bennu that it could operate safely in close proximity to a small, weakly gravitating body. A rare opportunity to watch a planetary-scale gravitational event reshape an asteroid in something close to real time, rather than inferring the process indirectly from a body that already looks however it's going to look by the time a spacecraft arrives. The capsule touched down within the expected landing zone, and roughly 120 grams of asteroid material, a modest amount by weight, but an enormous amount by scientific value, was recovered and flown to a specially built curation facility at NASA's Johnson Space Center in Houston. That facility is where the real work began, and it's worth understanding why it exists at all, because sample curation is its own quiet branch of planetary science. The entire point of a sample return mission, as opposed to a rover simply analyzing rock in place, is to get material into a laboratory on Earth where instruments far more sensitive and varied than anything you could fly on a spacecraft can be brought to bear. But that only works if the sample is protected from Earth's own atmosphere, moisture, and biological contamination the entire time, because contamination would make it impossible to tell native asteroid chemistry apart from something that leaked in during handling. So the Bennu sample is stored and manipulated inside sealed glove boxes, continuously flushed with nitrogen, a gas that won't react with the delicate organic chemistry inside, with every tool sterilized and every step documented so results can be checked against contamination controls. In practice, that international distribution has meant sending sealed, individually tracked portions of the Bennu sample to laboratories in Japan, the United Kingdom, France, and elsewhere, alongside the teams working directly at Johnson Space Center. A deliberate echo of the arrangement Japan's own space agency used when it shared portions of the Ryugu sample with NASA scientists after Hayabusa 2 return, so that both missions' material could be cross-analyzed by overlapping sets of international researchers using comparable instruments. Small portions have since been distributed to laboratories around the world for independent analysis, a deliberate structural choice, because a single group finding something extraordinary is a lot less convincing than a dozen independent groups confirming it using different instruments and different methods. That's what peer-reviewed actually looks like in practice. Not one paper, but a slow accumulation of independently checked results published over the following 2+ years, several of the most important of which only appeared in 2024 and 2025. The first major finding, announced in stages through late 2023 and into 2024, concerned organic chemistry. Analysis of Bennu's dust turned up 14 of the 20 amino acids that terrestrial life uses to build proteins. It turned up all 5 nucleobases that make up DNA and RNA, adenine, guanine, cytosine, thymine, and uracil, the molecular letters of genetic information. It turned up ammonia and phosphorus-bearing compounds, along with a wide range of other carbon and nitrogen-rich organic molecules. To be direct about what this does and doesn't mean, because NASA's own scientists have been unusually blunt on this point, none of it is evidence of life, or even evidence that life could have started on Bennu specifically. Amino acids are not proteins, and nucleobases are not DNA. They're simpler building blocks, the individual bricks rather than the building. What the finding does establish is that the raw chemical ingredients for biology aren't rare or exotic. They were apparently common enough in the early solar system that ordinary asteroids were manufacturing and stockpiling them, wholesale, long before Earth had oceans capable of receiving anything. The second major finding, published in Nature in early 2025 after additional detailed mineralogical analysis, is in some ways the more surprising of the two, because it's not about organic chemistry at all, it's about water. Researchers identified an evaporite sequence inside the Bennu samples. Layered sodium-bearing carbonates, phosphates, sulfates, chlorides, and fluorides, minerals that on Earth form through one specific, well-understood process, salty water, brine, evaporating slowly over an extended period, leaving mineral residues behind in the order their solubility dictates, the way a drying lakebed leaves rings of salt. Finding that same layered mineral signature inside asteroid material means the parent body Bennu broke off from likely a larger asteroid, perhaps 100 kilometers across, shattered in a collision sometime in the deep past, once held pockets of liquid water inside it, not briefly. Long enough and stable enough for that water to work as an active chemical environment, altering the surrounding rock and eventually drying out entirely, leaving a mineral fingerprint frozen in place for a few billion years until a spacecraft's sample arm happened to touch the right patch of gravel. That's a genuinely strange thing to picture. Wet chemistry running for an extended stretch of time inside a rock in the asteroid belt, with no sunlight reaching it and no atmosphere holding heat in, kept liquid only by warmth from the decay of short-lived radioactive isotopes and the residual heat of impacts. It tells scientists that the conditions for aqueous chemistry happening in liquid water, which is generally considered a near requirement for the kind of complex reactions that could eventually lead toward biology, weren't confined to planets with oceans and atmospheres. They may have been closer to routine throughout the early solar system's asteroid population, playing out inside countless small bodies that never got the chance to become planets at all. It's worth pausing on how thoroughly this result had to be checked before anyone was comfortable publishing it, because that process is itself part of the story. Mineral identification of this precision requires techniques like X-ray diffraction, which fires X-rays at a sample and reads the resulting diffraction pattern to identify crystal structure at the atomic level, along with electron microscopy, capable of resolving features far smaller than a human hair is wide. Different labs, using different instruments on different portions of the same sample, needed to converge on compatible conclusions before the evaporite finding could be published with confidence. And the process of coordinating that, cross-checking it, and writing it up for a journal like Nature took the better part of a year after the sample capsule landed. That's not a flaw in the system. That's the system working as intended. Extraordinary claims get tested from more than one direction before they enter the permanent scientific record. The sample kept producing results well into 2025, and some of the newer findings pushed the story of Bennu even further back in time than the evaporite minerals alone had suggested. Detailed isotopic and mineralogical work identified prosolar grains embedded within the sample, tiny mineral fragments that condensed around dying stars before our own sun ever ignited, meaning some of the material inside Bennu is, quite literally, older than the solar system it now orbits within. Separate analysis of a hot water extract from the sample turned up an unexpectedly large abundance of ammonia, a detail that matters because ammonia ice only condenses and survives in very cold environments, pointing to a formation region for Bennu's parent body out beyond the orbit of Jupiter, in the cold outer reaches of the early solar system, rather than anywhere near where the asteroid orbits today. That's consistent with a broader picture emerging from comparisons between Bennu and Ryugu, the carbonaceous asteroid sampled by Japan's Hayabusa 2 mission in 2020. A 2025 paper in Nature Communications, cross-analyzing material from both missions, argued that objects like these may represent some of the actual raw ingredients that were later swept up and incorporated into the rocky planets, Earth included, as the solar system finished assembling itself. The phosphate story also kept developing. Earlier analysis had already flagged an unusual magnesium-sodium phosphate mineral in the Bennu sample, a compound that had shown up once before, in trace amounts, in the Ryugu sample, but that appeared in the Bennu material with a purity and grain size that mission scientists described as unprecedented in any meteorite ever studied, natural, or fallen to Earth. Continued work through 2025 identified an even wider family of related compounds sitting inside the same clay-rich matrix. A mix of carbonates, water-rich and nitrogen-rich mineral phases, and hydrated grains combining ammonium, magnesium, and phosphorus in structures that hadn't been cataloged in extraterrestrial material before. On the organic side, researchers also identified tryptophan among the amino acids present in the sample. Significant because tryptophan hadn't previously turned up in any meteorite or returned asteroid sample, despite decades of searching, making Bennu's inventory of life's chemical building blocks a little more complete than scientists had established even a year earlier. A separate 2025 paper examining how that organic chemistry was distributed through the sample found evidence of what researchers termed heterogeneous aqueous alteration, meaning the water that once moved through Bennu's parent body didn't process the rock evenly, leaving pockets of more and less altered material sitting side by side, a level of chemical detail that simply wasn't accessible before an actual physical sample existed to study grain by grain. There is also a decidedly practical reason NASA cared about Bennu specifically, beyond its scientific value as a time capsule. Bennu's orbit brings it uncomfortably close to Earth on a regular basis, and long-term orbital modeling, refined using tracking data gathered by OSIRIS-REx itself during its 2 years in close proximity to the asteroid, puts Bennu on a list of the more notable known long-term impact risk objects, with a cumulative probability, spread out over multiple potential close approaches between now and the year 2300. That remains small in absolute terms but non-zero enough that scientists take it seriously. Understanding precisely what Bennu is made of, how it holds together, how it would respond to any future deflection attempt, how porous or dense the interior isn't just abstract curiosity. It's the same kind of information planetary defense planning would need if humanity ever had to alter the path of a hazardous asteroid, and Bennu's rubble pile structure, confirmed so dramatically when the sample arm sank into it during collection, suggests such objects may be far more fragile and unpredictable to interact with than earlier models assumed. Multiple papers analyzing the Bennu samples are still moving through peer review as of this recording, with researchers still working through the roughly 2/3 of the sample that's been deliberately set aside and preserved, untouched, for future scientists with instruments that don't exist yet. A strategy borrowed directly from how NASA handled the Apollo moon rocks, some of which sat sealed and unopened for decades, until analytical techniques caught up to what scientists wanted to ask them. Bennu, in other words, isn't a finished story. It's an archive that will keep generating new results for years, maybe decades to come. Part 2: The Ocean Beneath the Ice. If Bennu is a story about small, ancient objects and the chemistry preserved in their gravel, Europa is the opposite kind of story. A story about an active, ongoing environment, roughly the size of Earth's own moon, wrapped around one of the solar system's largest planets, that scientists have suspected for decades might be one of the more promising places in the entire solar system to look for the conditions life requires. Europa was discovered by Galileo Galilei in 1610, one of the 4 large moons of Jupiter that still bear his name collectively, the Galilean moons. For most of the time since, it was just a point of light, a small disk, notable mainly for its unusually high reflectivity, brighter and smoother looking than almost any other body in the solar system. It wasn't until the Voyager flybys of 1979, and much more thoroughly the Galileo orbiter mission through the 1990s and into the early 2000s, that scientists began piecing together what that brightness meant. Europa's surface is almost entirely water ice, a shell laced with long, reddish-brown fractures called linnae that stretch for hundreds of kilometers, evidence of a crust under constant mechanical stress. Galileo's magnetometer data, in particular, provided strong indirect evidence, through the way Europa's induced magnetic field responded to Jupiter's much larger one, that a layer of electrically conductive fluid, almost certainly salty liquid water, exists beneath that ice shell. Best estimates put that subsurface ocean at containing roughly twice the volume of water in all of Earth's oceans combined, kept from freezing solid by tidal heating. The way Jupiter's gravity, combined with the gravitational tug of the neighboring moon Io, continuously flexes and kneads Europa's interior as it orbits, generating enough frictional heat to sustain a liquid layer beneath dozens of kilometers of ice. What Galileo and the telescopes that followed it couldn't do was tell scientists much about that ocean's actual chemistry, what's dissolved in it, whether it has the kind of carbon and energy sources that would make it chemically hospitable rather than simply liquid. You can't send a submarine through dozens of kilometers of ice on a first attempt, and even detecting a faint chemical signature from a moon 400 million miles away, filtered through Jupiter's own brightness and radiation environment, is a genuinely difficult observational problem. That's the gap the James Webb Space Telescope was positioned to help close. Webb, launched in December 2021, and operating from a stable orbit around a gravitational balance point called the second Sun-Earth Lagrange point, roughly 1 million miles from Earth in the opposite direction from the Sun, carries instruments built around infrared spectroscopy, essentially splitting incoming infrared light from a distant object into its component wavelengths and reading which wavelengths are missing or enhanced. Because different molecules absorb and emit infrared light at very specific, identifiable wavelengths, the way a fingerprint identifies a person. That technique traces directly back to a cruder version of the same idea Galileo used indirectly at Europa decades earlier. Galileo's magnetometer detected an induced magnetic field by watching how Europa's own local field responded, in a kind of sympathetic wobble, to the much larger rotating field generated by Jupiter itself. A response that only makes sense if a layer of electrically conductive material, almost certainly salty liquid water, sits inside Europa reacting to Jupiter's field the way a coin held near a magnet reacts to it. It was a clever, entirely indirect measurement, good enough to establish that an ocean was there, but never capable of saying much about what was dissolved inside it. Spectroscopy is what filled that specific gap, where the magnetometer could only sense the ocean's electrical behavior as a whole. Infrared spectroscopy from Webb could pick out individual molecules on the surface directly above it, one absorption line at a time. In September 2023, a team using Webb's NIRSpec instrument turned that capability toward Europa and detected carbon dioxide on the moon's surface. Not a huge surprise on its own, since carbon dioxide ice has been suspected there before, but the distribution was the genuinely important part. The carbon dioxide wasn't spread evenly across Europa. It was heavily concentrated in a specific region called Terra Regio, an area of unusually young, jumbled, chaotic terrain where the surface ice shows clear evidence of having been disrupted and reworked from below relatively recently. In geological terms, potentially within the last few 100,000 years, which for a body billions of years old is essentially yesterday. That concentration matters scientifically because it lets researchers rule out, or at least argue strongly against, one obvious alternative explanation. If the carbon dioxide had arrived from outside, delivered by comet or meteorite impacts, the way some surface chemistry on airless bodies does, you'd expect it to be scattered relatively evenly or clustered around impact sites, not concentrated specifically in a geologically young, geologically active-looking region. Instead, the pattern is consistent with carbon that originated in the ocean beneath the ice and reached the surface through some kind of resurfacing or venting process, carrying with it a chemical signature of what's actually down there. Carbon is one of the handful of elements considered essential, non-negotiable, for the kind of chemistry life as we understand it depends on. So finding it apparently sourced from inside Europa's ocean, rather than delivered from outside, is a real, if preliminary, clue about what that hidden sea might be chemically capable of supporting. In the same set of observations, Webb also picked up tentative signs of hydrogen peroxide on the surface, a compound relevant to oxidation chemistry that could matter for the ocean's habitability. Though the mission scientists involved have been careful to describe that particular signal as needing further confirmation, not as a settled result, and follow-up observations are ongoing. That interpretation didn't go unchallenged, and it's worth walking through why, because the back and forth is itself part of how this kind of finding gets confirmed. Some researchers examining the same Webb dataset argued the carbon dioxide could still be explained by processes confined to the surface itself, sunlight-driven chemistry reworking older, buried carbon dioxide ice without requiring any direct connection to the ocean below. Resolving that disagreement required additional spectral analysis of the exact distribution and depth of the CO2 signal, cross-checked against independent modeling of how quickly surface ice at Europa's temperatures would need to be replenished to match what Webb observed. Modeling that, on balance, has continued to favor a subsurface source, though the mission scientists involved have stopped short of calling it settled. That's exactly the kind of open question Europa Clipper's own ice-penetrating radar and magnetometer are being sent to help close directly, rather than by continuing to argue over a single remote spectrum. It's worth being precise about what this finding is not. It is not a detection of an ocean that was already established. It is not a detection of organic molecules or biosignatures or anything resembling direct evidence of biology. It's a chemistry result, evidence about the composition of a system we already knew existed, adding one more piece to an unfinished picture. That distinction is exactly why NASA had already committed, well before this specific Webb observation, to sending a dedicated spacecraft to investigate Europa directly. That spacecraft, Europa Clipper, launched in October 2024 aboard a Falcon Heavy rocket, and it is, remarkably for a mission headed to the outer solar system, the largest spacecraft NASA has ever built for planetary exploration, with solar arrays spanning about 100 feet across, oversized specifically because sunlight at Jupiter's distance is roughly 1/25th as intense as at Earth. So Clipper needs an enormous collecting area just to generate enough power to run its instruments. Clipper's route to Jupiter isn't a straight line. It's using a Mars gravity assist flyby followed by an Earth gravity assist flyby, a sequence that lets the spacecraft essentially borrow orbital momentum from those planets to reach Jupiter using far less fuel than a direct trajectory would require, with arrival expected in 2030. Once there, Clipper will not land, and that's a deliberate design decision, not a limitation the mission simply accepted. Jupiter's magnetic field traps enormous quantities of charged particles into intense radiation belts, and Europa sits well within that punishing environment. A stationary lander would face a radiation dose severe enough to disable its electronics within a relatively short operational window. Instead, Clipper will settle into a long, looping orbit around Jupiter itself, and perform approximately 50 close flybys of Europa over the course of its prime mission, diving in close for each pass, and then retreating to a safer distance, where its electronics can recover before the next encounter. A strategy that trades a shorter cumulative time near Europa for a dramatically longer operational lifespan than a lander or an orbiter that stayed close continuously could achieve. The instrument suite is built specifically to chase the questions Galileo and Webb could only partially answer. A pair of spectrometers will map surface composition in far greater detail than Webb's Earth orbit vantage point allows, hunting for exactly the kind of localized chemical signatures, like the Tara Regio carbon dioxide, that suggest ongoing communication between the ocean and the surface. An ice-penetrating radar instrument will attempt to directly measure the thickness of the ice shell and search for pockets of liquid water trapped within it, closer to the surface than the main ocean. A magnetometer, building directly on the technique Galileo used indirectly decades ago, will measure Europa's induced magnetic field with far greater precision, allowing scientists to calculate the ocean's depth and, critically, its salinity, a rough proxy for how chemically active and potentially habitable that hidden water might be. A thermal imager will scan for anomalously warm spots on the surface, possible sites of active plume venting, similar to what's been observed at Saturn's moon Enceladus, which we'll come back to shortly. None of Clipper's instruments are designed to detect life directly. There's no biology experiment on board in the way you might imagine from science fiction. Its entire mission is designed to answer a narrower, more answerable question. Does Europa actually have the conditions that could support life, as best as we can determine from orbit? The chemistry, the energy sources, the stability of the ocean environment over geological time. Webb's carbon dioxide detection didn't answer that question. What it did was hand the Clipper science team a specific, real, geographically located target, Tara Regio, and similar young terrain, worth prioritizing once the spacecraft actually arrives and starts choosing where to point its instruments. Part 3. The ice giants we'd almost forgotten. Before we leave the outer solar system and head somewhere considerably hotter, it's worth spending time on two planets that rarely get much attention, mostly because so little data about them exists in the first place: Uranus and Neptune. Both ice giants have been visited by exactly one spacecraft, ever Voyager 2, which flew past Uranus in January 1986 and Neptune in August 1989, gathering, in each case, a matter of hours of close-up data before continuing outward, forever, into the interstellar mission we'll discuss later in this program. Everything humanity learned about these two planets up close, we learned in those two brief windows nearly 40 years ago. Everything since has come from telescopes working at enormous distances, through Earth's atmosphere, or, since 2021, from Webb's considerably clearer vantage point in space. Webb's observations of Uranus, gathered across several sessions since 2023, produced some genuinely startling imagery. Using long-exposure infrared imaging, Webb captured 11 of Uranus's 13 known rings, several of them so faint made of dark, fine dust rather than the icy, reflective material that makes Saturn's rings so bright, that they're difficult to detect even with the Hubble Space Telescope, which has been observing Uranus for decades. Webb also imaged a bright, energetic polar cap over Uranus's pole, one that appears to brighten and shift in structure as the planet's seasons change. And Uranus's seasons are unlike anything else in the solar system, because the planet's rotational axis is tipped over almost 98 degrees relative to its orbit, essentially rolling around the sun on its side rather than spinning upright like Earth. That extreme tilt is generally attributed to some ancient, catastrophic collision early in the planet's history, though the details remain genuinely uncertain. One consequence of that tilt is an 84-year orbital period paired with correspondingly extreme seasons. A pole can spend decades in continuous sunlight, then decades in continuous darkness, and Webb is now watching that polar cap evolve in ways that don't fully match the atmospheric models scientists had built from the limited Voyager and Hubble data, including unexpectedly bright, energetic storm activity near the pole that researchers are still working to explain. At Neptune, Webb's contribution has been similarly significant. Infrared imaging released in 2023 resolved Neptune's dusty, difficult-to-see ring system in the clearest images obtained since Voyager 2's 1989 flyby, a genuinely long gap to close. Separate observations, comparing Webb's infrared data against decades of earlier ground and space-based measurements, revealed that Neptune's upper atmosphere had mysteriously cooled by several hundred degrees Fahrenheit over the preceding 2 decades. A substantial and unexplained shift for a planet whose atmospheric temperature scientists had assumed was relatively stable, alongside an unexpected warm spot detected at Neptune's south pole. Neither the cooling trend nor the polar hotspot has a fully settled explanation yet. Both remain active areas of research, with several competing hypotheses involving seasonal effects, atmospheric chemistry, and Neptune's own multi-decade orbital cycle around the Sun, which at roughly 165 years means we've observed less than one complete Neptune year since the planet's discovery in 1846. None of these individual results carry quite the same headline weight as an ocean moon's chemistry or a stellar flyby, but they matter for a structural reason that's easy to overlook. Uranus and Neptune are, by a wide margin, the least explored planets in the solar system. Every other planet has had multiple dedicated missions, in some cases dozens. These two ice giants have had exactly one spacecraft pass through, decades ago, for hours at a time. That means every new observation, however incremental it might look next to a Europa or a Bennu, is disproportionately valuable, simply because there's so little existing data to compare it against and so much still genuinely unknown. It's part of why NASA and the broader planetary science community have, in recent years, identified a dedicated orbiter mission to Uranus as one of the highest priorities in the field's decadal survey process. The formal, community-wide ranking exercise that shapes what gets funded over the following 10 years. Though such a mission, if it proceeds, remains a matter of years away from launch, let alone arrival. That priority ranking isn't abstract. Planetary scientists have already produced a detailed design, called the Uranus Orbiter and Probe, built around dropping an atmospheric probe into Uranus shortly after arrival, and then using a sequence of flybys of the moon Titania to gradually bend the orbiter's path down into the planet's equatorial plane, setting up a multi-year tour past all 5 of Uranus's major moons. Under the mission's current design studies, the most efficient path there would use a gravity assist from Jupiter, available during launch windows identified for June 2031 and April 2032, bending a roughly 5,000-kilogram spacecraft onto a trajectory that would still take about 13 years to reach Uranus even with that boost. A reminder of just how far out these two ice giants actually sit, and why. Even with a favorable decadal survey ranking and a completed engineering study in hand, nobody currently watching this program should expect a launch, let alone new close-up data, before the early 2030s at the earliest. Part 4. Into the Sun's atmosphere. Now we leave the outer solar system entirely and go somewhere that, on the surface, sounds like it should hold no mysteries at all, because it's the one object in the sky humans have been staring at since before we had written language: the Sun. The idea behind NASA's Parker Solar Probe traces back decades to an unresolved problem in solar physics that had been sitting there, essentially unchallenged, since the 1940s. The Sun's visible surface, the photosphere, sits at a temperature of roughly 10,000 degrees Fahrenheit, but the corona, the wispy, ghostly outer atmosphere you can normally only see with the naked eye during a total solar eclipse, when the moon blocks out the blinding disk of the Sun itself, runs hundreds of times hotter, into the millions of degrees. That's backwards from how heat is supposed to behave. Moving farther from a heat source should mean things get cooler, not dramatically hotter, and for the better part of a century nobody could adequately explain why the corona breaks that rule. Answering it properly required more than remote observation from telescopes. It required a spacecraft that could actually fly into the corona and take direct measurements of the plasma and magnetic fields there. That's an extraordinarily difficult engineering problem, which is part of why the mission took decades to become technically feasible. Parker Solar Probe, named after the astrophysicist Eugene Parker, who first theorized the existence of the solar wind back in 1958, launched in August 2018, and has spent the years since executing a long, patient sequence of gravity-assist flybys of Venus, 7 of them across the mission, each one trimming a little more energy from its orbit and drawing its closest approach to the Sun progressively tighter. Rather than attempting a single direct dive that would have been both far more fuel-expensive and far riskier. Surviving proximity to the Sun required solving a heat problem, unlike anything NASA had previously engineered around. Parker's heat shield, a carbon composite panel about 8 feet across called the thermal protection system, is built to endure temperatures approaching 2,500 degrees Fahrenheit on its sunward face during closest approach, while the spacecraft's instruments, tucked in the shadow directly behind that shield, remain close to room temperature throughout, a temperature differential across a few feet of spacecraft that is, by itself, one of the more remarkable pieces of engineering in the history of American spaceflight. The shield isn't simply insulation. Its design relies on the shape and angle of approach, keeping the instrument-bearing side of the spacecraft continuously in shadow, meaning the mission's entire trajectory has to be planned around maintaining that geometry precisely across every close pass. None of that heat shield performance was ever going to be something engineers could simply calculate on paper and trust. Before Parker ever launched, full-scale sections of the thermal protection system were tested in ground facilities capable of simulating solar heating far beyond anything the shield would actually encounter near Earth, including specialized furnaces and plasmark test chambers built to replicate the specific combination of extreme radiant heat and particle bombardment the spacecraft would face at closest approach, because there was no way to send a prototype on a cheap, low-stakes rehearsal flight first. The first time the actual flight hardware would ever experience real solar heating anywhere close to the mission's design limits was going to be the real mission, with the real spacecraft, and no opportunity for a do-over if the shield failed. That's a category of engineering risk most Earth-orbiting or even planetary missions don't have to accept in quite the same way. And it's part of why Parker Solar Probe took the better part of a decade to move from approved concept to actual launch. On December 24, 2024, Christmas Eve, a Parker Solar Probe reached its record closest approach to date, passing within roughly 3.8 million miles of the Sun's surface, or about 6.1 million kilometers. To put that distance in context, Mercury, the innermost planet, orbits more than 10 times farther from the Sun than that. At that distance, Parker was traveling at roughly 430,000 miles per hour relative to the Sun, fast enough to cross the continental United States, New York to Los Angeles, in under 30 seconds, which made it, at the moment of that pass, unambiguously the fastest object human beings have ever built. The spacecraft repeated that same closest approach distance and speed twice more, on March 22, 2025, and again on June 19, 2025, which marked the 24th and final perihelion of Parker's originally planned primary mission, though final in this case doesn't mean the mission ended. With the spacecraft healthy and its trajectory stable, NASA has continued operating Parker in an extended phase, with additional close passes continuing on roughly the same repeating orbital geometry. Funding for continued operations currently projected through the end of the decade. The point of flying this close was never simply to set a speed or proximity record, even though both make for a good headline. The scientific purpose was to fly directly through the corona and sample it in place, measuring the plasma, the magnetic field structure, and the particle behavior directly, rather than inferring it from a distance the way every solar physicist before Parker had been forced to. That direct sampling has already produced results that reshaped how scientists think about the solar wind. The continuous stream of charged particles the Sun sends outward through the entire solar system. Early in the mission, Parker's instruments confirmed the existence of small-scale magnetic structures nicknamed switchbacks, brief, sharp zigzag reversals in the direction of the Sun's magnetic field embedded within the solar wind, whipping past the spacecraft in bursts. Switchbacks had been hinted at in earlier, more distant spacecraft data, but Parker was able to confirm their common, measure their structure directly, and tie them to specific processes happening down at the base of the corona, closer to the Sun's surface. A step that matters directly for the coronal heating question, since one leading hypothesis holds that this kind of small-scale magnetic reconnection, the snapping and reconnecting of magnetic field lines, could be dumping enough energy into the corona to explain at least part of why it runs so much hotter than the surface below it. That result mattered on a personal level too, in a way that's easy to miss in the raw data. Eugene Parker, the mission's namesake, had proposed the existence of a continuous outward flow of charged particles from the Sun back in 1958, an idea much of the physics establishment initially dismissed as implausible, since the mathematics of the time suggested the corona should be too gravitationally bound to the Sun to escape outward as a steady wind. Parker was proven right within a few years, once early spacecraft directly measured the solar wind he'd predicted, but the deeper question of what actually accelerates and heats that wind as it leaves the corona remained open for the rest of his life. Parker died in March 2022, less than 4 years after the spacecraft bearing his name launched, but still well within the mission's active data-gathering phase, meaning he lived to see his own probe flying closer to the Sun than any spacecraft in history. Though the closest approaches described earlier in this program, the December 2024 through June 2025 sequence, all happened after his death, achieved on an orbit that continues to tighten slightly with each remaining Venus flyby, with mission funding currently extending operations through the rest of this decade, and additional record-setting passes still on the schedule. Even though the switchback measurements that may finally help explain the mechanism he spent a career trying to identify were still being worked through by the time of his death, and remain, in refined form, one of the central open questions the mission continues to chase with every subsequent close pass. Mission scientists have been consistently upfront that the data from the very closest passes, the December 2024 through June 2025 sequence, is still being worked through in detail, and that some of the more specific conclusions about coronal heating mechanisms and solar wind acceleration will take additional time, additional papers, and additional cross-checking against earlier passes before the community settles on firm answers. That's not a delay caused by anything going wrong. It reflects the sheer volume and complexity of the data, a spacecraft moving at 430,000 miles per hour through a stellar atmosphere can gather in the space of a few hours, and how much careful analysis is required to turn that raw stream of measurements into physical understanding anyone can rely on. But the raw achievement, a human-built spacecraft repeatedly surviving direct passage through the atmosphere of a star, its heat shield holding, its instruments functioning, its trajectory precisely maintained across each close approach, is already a matter of historical record, independent of exactly how the remaining analysis resolves. Part 5. The Moon that sprays its ocean into space. Let's go back out to the outer solar system for a moment, because Europa isn't the only icy moon with a hidden ocean, and it isn't the only one Webb has had something new to say about. Saturn's moon Enceladus is considerably smaller than Europa, only about 500 kilometers across, roughly the width of Arizona, but it's been one of the most closely watched objects in planetary science since NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, made an unexpected discovery early in its mission: geysers. plumes of water vapor and ice particles erupting from a set of long fractures near the Moon's south pole, nicknamed tiger stripes for their parallel, striped appearance, venting material directly out of Enceladus's interior into space. Cassini flew directly through some of those plumes on later passes, close enough to directly sample the material with onboard instruments, and confirmed they contained water vapor, ice grains, simple organic compounds, and significantly molecular hydrogen, a finding that suggested active hydrothermal chemistry happening at Enceladus's rocky core, similar in principle to the hydrothermal vents on Earth's own ocean floor that support entire ecosystems independent of sunlight. Cassini made those detections using an instrument called the ion and neutral mass spectrometer, built to catch gas molecules streaming directly into it as the spacecraft flew through a plume at several kilometers per second, sorting them by mass to identify which molecules were present and in roughly what proportion. A genuinely difficult measurement to make well. Since the spacecraft was never designed as a dedicated plume sampling instrument and had to be repurposed for a kind of encounter nobody had fully planned for when Cassini first launched in 1997, years before anyone knew Enceladus was venting anything at all. What Cassini couldn't easily do, orbiting Saturn rather than sitting at a distance, was capture the full three-dimensional scale of those plumes in a single view. That's where Webb came in. In observations released in 2023, Webb's NIRS-SPEC instrument captured a plume from Enceladus extending an almost startling 6,000 miles from the Moon's surface, more than 40 times Enceladus's own radius, far larger than any single previous observation had captured, essentially confirming that the Moon's venting is even more extensive than the Cassini-era plume maps had suggested. Webb's data indicated water vapor escaping at a rate of roughly 300 liters per second, and in a detail that mattered for understanding Saturn's broader ring and moon system. The observations showed that while roughly 30% of that vented water falls back onto Enceladus's own surface, the remaining 70% escapes entirely, spreading out to form a vast, faint torus of water vapor that effectively feeds material into a broad donut-shaped region of Saturn's magnetosphere, and ultimately contributes to Saturn's diffuse outer E-ring, one of the planet's faintest and least understood rings. The significance here runs parallel to Europa's. Enceladus is now understood to be actively, continuously venting material from its subsurface ocean directly into space, where it can be sampled from a distance without ever having to drill through kilometers of ice. That's part of why Enceladus sits, alongside Europa, near the top of essentially every list of priority targets in the search for habitable environments beyond Earth. The ocean is not just there. It is, in a sense, advertising its own chemistry. NASA does not currently have a dedicated Enceladus mission funded, and in development the way Europa Clipper exists for Europa, though mission concepts aimed specifically at flying through the plumes and directly analyzing their organic content in far greater detail than Cassini's more limited instrumentation allowed, have been proposed and studied repeatedly by the planetary science community, and remain among the most frequently discussed future flagship-class mission candidates. One of those proposed concepts has a name and a fairly detailed design already attached to it. Enceladus Orbilander, a flagship-class mission studied specifically for NASA's 2023 Planetary Science Decadal Survey, the same community-wide prioritization process that flagged Uranus as the top new flagship destination. Orbilander's design is unusual for a flagship concept in that a single spacecraft would do two jobs in sequence, spending roughly a year and a half in orbit around Saturn's system studying Enceladus and its plumes from a distance, before eventually descending and landing directly on the surface near the tiger stripe fractures, close enough to sample fresh plume fallout accumulating on the ice, and operate there for a further 2 years. Its notional instrument package, built around what mission planners call a life detection suite, would include 5 separate, complementary instruments designed to search for biosignatures using different, independent methods, on the theory that no single instrument's result would be considered convincing enough on its own. The same insistence on independent cross-confirmation that shaped how the Bennu sample was analyzed, just applied to the search for life instead of the search for water. In the Decadal Survey's own ranking, Orbilander came in as the second highest priority flagship concept, just behind the Uranus mission, meaning that if funding ever allows both to proceed, Enceladus's actively venting ocean could eventually get the kind of direct, landed scrutiny that Europa's currently hidden one cannot receive, until scientists find a way to get through several miles of ice. Part 6. The Time Capsule's SHARING Jupiter's Orbit. There's a population of asteroids that doesn't get nearly the public attention that Bennu, or the main asteroid belt, gets, and it's worth understanding why NASA committed an entire dedicated mission to visiting them. Scattered along Jupiter's orbital path, clustered in two swarms roughly 60 degrees ahead of and behind the planet itself, at gravitationally stable points called Lagrange points, sit thousands of objects known as the Jupiter Trojans. They're not moving toward or away from Jupiter. They're locked into Jupiter's orbit, riding along with the planet in a gravitational balancing act first worked out mathematically by Joseph Louis Lagrange in the 18th century, long before anyone knew such objects actually existed out there. What makes the Trojans scientifically valuable isn't their strange orbital arrangement on its own. It's what current solar system formation models suggest about their origin. Many Trojans are thought to be objects that formed much farther out, in the colder outer solar system near or beyond where Neptune sits today, and were gravitationally shepherded into their current positions during a period of orbital rearrangement among the giant planets billions of years ago. If that's correct, the Trojans function as a genuinely diverse sample set, a scattered library of building blocks from very different regions of the early solar system, all now conveniently, if only in relative terms, clustered along a single planet's orbit. NASA's mission to study them, named Lucy after the famous 3.2-million-year-old hominin fossil discovered in Ethiopia in 1974, itself named after the Beatles' song Lucy in the Sky with Diamonds, which the Discovery team happened to be listening to on the night they found it, launched in October 2021. The naming choice reflects the mission's central idea directly. Just as the Lucy fossil offered a rare, direct look at a crucial, and otherwise poorly understood stage in human evolution, the Lucy spacecraft is meant to offer a direct look at the building blocks of planetary formation, preserved essentially unchanged since the early solar system. That launch, however, didn't go entirely according to plan. And the fix is worth understanding, because it's a good example of how mission teams handle a problem that can't simply be sent back to the shop for repair. Shortly after Lucy separated from its rocket in October 2021, one of its two circular solar arrays, each about 24 feet across, needed to power the spacecraft across distances where sunlight is far too weak for a smaller array to suffice, failed to fully unfold and click into its final locked position. Engineers eventually traced the likely cause to a lanyard, part of the deployment mechanism, that lost tension during unfolding and slipped off its spool, wrapping around the motor shaft it was supposed to be pulling taut. Over several months in 2022, the team attempted a careful, repeated sequence of motor pulses designed to work the array further open without risking damage to the mechanism, eventually coaxing it to somewhere between 353 and 357 degrees of a full 360-degree deployment. By January 2023, engineers concluded further attempts carried more risk than benefit, and made the call to stop trying, accepting the array in its current tension but unlatched state, a state their models indicated was already collecting over 98% of the power a fully latched array would provide, more than enough to run the spacecraft and its instruments safely through the encounters that followed, including both rehearsal flybys and, eventually, the Trojans themselves. Lucy's flight plan is genuinely unlike any previous planetary mission. Over its 12-year primary mission, it's designed to visit 8 different asteroids using a complex sequence of Earth gravity-assist flybys to reshape its orbit repeatedly, including one target in the main asteroid belt between Mars and Jupiter as essentially a warm-up, followed by 5 Trojans clustered around Jupiter's leading Lagrange point. Then a return swing back past Earth to redirect out to 2 more Trojans, including a binary pair. Trailing behind Jupiter at the opposite Lagrange point, no other single spacecraft has ever been targeted at this many separate small-body destinations. The main belt warm-up target was an asteroid called Dinkinesh, the Ethiopian name for the Lucy fossil itself, meaning roughly, "You are marvelous" in Amharic. And the flyby on November 1, 2023, was originally added to the mission timeline specifically as an engineering test, a chance to exercise the spacecraft's autonomous asteroid tracking system on a real target before the higher-value Trojan encounters. It ended up delivering a real scientific surprise instead. As Lucy approached, its cameras revealed that Dinkinesh has a small companion, a satellite roughly the size of a few hundred meters across, not unusual on its own, since a meaningful fraction of asteroids turn out to have small moons once anyone looks closely enough. What was unusual is that the satellite, later named Selam, turned out itself to be a contact binary, 2 separate smaller lobes touching each other, essentially 2 objects gently stuck together rather than one solid body, the first contact binary satellite of an asteroid ever directly observed. It's a small discovery in absolute terms, but it's exactly the kind of finding that illustrates why flying past objects up close, rather than relying purely on ground-based telescope observations, keeps turning up structure nobody predicted. Lucy's second close encounter came in April 2025 with an asteroid called Donald Johanson, named for the paleoanthropologist who discovered the original Lucy fossil, another deliberate rehearsal ahead of the Trojan encounters proper, timed specifically to test the spacecraft's systems once more before the higher-stakes flybys began. The images returned showed a strikingly elongated object, roughly 8 kilometers along its long axis, with a pinched, almost peanut-shaped waist near its middle, consistent with a slow, gentle collision history rather than a violent one. Ground-based telescope observations beforehand had already picked up regular brightness fluctuations, suggesting an elongated shape rotating roughly once every 10.5 Earth days, and the close-up imagery confirmed and considerably sharpened that picture. Scientists have been particularly interested in comparing Donald Johanson's composition and structure against Bennu and against Ryugu, the asteroid sampled by Japan's Hayabusa 2 mission, since all 3 appear to be carbonaceous, water and organic-bearing bodies, but with different collisional histories that may help explain why their surfaces and internal structures differ as much as they do. The main event for Lucy is still ahead of it. The spacecraft's first flyby of an actual Jupiter Trojan, the asteroid Uranus and its own small satellite Quetta, is scheduled for August 2027, and that particular target was chosen deliberately, because earlier ground and space-based observations had already identified Uranus as the largest known member of a Trojan collisional family, a cluster of asteroids that share a common ancestor object broken apart in some past impact, making it a promising site for studying both the original parent body's composition and the physics of the collision that fragmented it. Collisional families like the one Uranus anchors are identified statistically, long before any spacecraft visits them, by clustering asteroids according to their orbital properties, semi-major axis, eccentricity, and inclination, since a single violent breakup scatters fragments onto orbits that stay recognizably similar to each other, and to the parent body's original path for a very long time afterward, in some cases for 1 billion years or more. Ground-based spectroscopy had already suggested Uranus, and its relatives share a common surface composition consistent with that shared origin. But only a close flyby can test whether the interior tells the same story, and whether the satellite Quetta is itself a genuine fragment of the original breakup or a later, unrelated capture. 4 additional Trojan encounters follow across the years after that, extending Lucy's primary mission out toward the early 2030s. For now, the mission remains in transit, its rehearsal flybys completed, and its instruments confirmed healthy, waiting on an encounter that's still roughly a year out from this recording. A reminder that some of the biggest results in this program are still ahead of us, not behind us. Part 7. A Journey to a World Made of Metal. If Bennu and the Trojans are time capsules of rock, ice, and organic chemistry, there's a very different kind of asteroid currently being approached by a NASA spacecraft, and it may represent something genuinely unique in the solar system, a piece of a planetary core. The asteroid Psyche, discovered in 1852 and orbiting within the main asteroid belt between Mars and Jupiter, stood out to astronomers for decades because of its density and its radar reflectivity. Indirect measurements suggesting it's unusually metal-rich compared to the vast majority of asteroids, which are dominated by rock and ice. The leading hypothesis, still not fully confirmed, is that Psyche may be the exposed metallic core of a much larger differentiated protoplanet, a body that, early in the solar system's history, grew large enough to melt internally and separate into layers the way Earth did, with heavy metals sinking to the center and lighter rock forming an outer mantle and crust, before some ancient, violent collision or series of collisions stripped away that outer rock layer entirely, leaving the dense metallic core exposed and drifting in the asteroid belt ever since. Current estimates suggest Psyche's composition is a mixture of metal and rock, with metal making up somewhere between 30 and 60% of its volume by current modeling, considerably more metal-rich than an ordinary rocky asteroid, though probably not the almost pure iron-nickel ball earlier, more simplified models once proposed. That range itself is the product of a real scientific argument that played out over the years leading up to launch. Earlier remote studies, working from Psyche's brightness, density, and radar reflectivity alone, had left room for models in which the asteroid was almost entirely metal. A more detailed synthesis published in 2022, folding in updated density estimates, thermal infrared measurements, and comparisons against known iron meteorites and sulfide minerals like troilite, argued for a plausible composition closer to 30 to 55% metal by volume, with the remainder made up of rocky silicate material and a substantial amount of open-pore space threaded through the interior. A genuinely more complicated object than the simple exposed core picture that first made Psyche famous. Psyche's measured thermal inertia, a property that describes how quickly a surface heats and cools as it rotates in and out of sunlight, came back higher than typical for a large asteroid, consistent with a denser, more metal-rich surface, but not so high that it rules out a porous, rubble-strewn exterior sitting above whatever lies beneath. Untangling exactly which version is closer to correct is precisely the kind of question that remote brightness measurements from Earth can only narrow, not answer, which is the entire reason the spacecraft is currently in transit at all. If that core remnant hypothesis holds up, Psyche would be genuinely unique in accessible reach of a spacecraft, the only place in the solar system where scientists could study planetary core material directly, without having to somehow drill 1,800 miles down through Earth's own mantle to reach our planet's actual core, something that remains, and likely will remain indefinitely, entirely beyond any realistic engineering capability. Everything scientists currently know about the composition and behavior of planetary cores, including Earth's own, comes from indirect methods: seismic wave behavior, magnetic field modeling, geochemical inference from meteorites believed to represent shattered protoplanet cores. a spacecraft actually orbiting and directly measuring a body that may be a real, physical planetary core, would be an entirely different category of evidence. NASA's Psyche mission launched in October 2023 aboard a Falcon Heavy rocket, using an ion propulsion system, a form of electric propulsion that generates thrust by accelerating charged xenon gas through an electric field, producing a very gentle but extremely fuel-efficient push, sustained continuously over long stretches of the voyage, rather than the brief, powerful burns a conventional chemical rocket would use. That efficiency comes with a real operational cost, though. In April 2025, engineers detected an unexpected drop in the pressure of the spacecraft's xenon propulsion system and paused thrusting entirely while investigating, eventually switching over to a backup fuel line to continue operations, with full thruster function restored by mid-June 2025. A reminder that even missions running smoothly on paper can require real-time troubleshooting across hundreds of millions of miles of distance and a substantial communication delay. Psyche also carries a piece of technology that has nothing to do with asteroids at all, but that may end up mattering just as much for the missions that come after it. Riding along with the science instruments is an experimental laser communications terminal called the Deep Space Optical Communications Demonstration, testing whether an infrared laser, rather than the radio signals every previous NASA deep space mission has relied on, can reliably carry far more data across the same enormous distances. The demonstration achieved first light, its first successful laser link with a ground station on Earth, on November 14, 2023, and less than a month later on December 11, transmitted a 15-second ultra-high-definition video back across roughly 19 million miles, a functional proof that the system worked at all. From there, the tests kept pushing distance and difficulty. A July 2024 trial confirmed the system could track and lock onto a laser signal in daytime conditions from 288 million miles away, and by December 2024, with Psyche nearly 494 million kilometers out, more than twice the distance between Earth and Mars at their farthest. The demonstration set its most distant successful link yet, sustaining data rates of up to 267 megabits per second. Faster than the ordinary terrestrial broadband connection, linking the receiving ground station to mission control at NASA's Jet Propulsion Laboratory. Over the roughly 2 years it ran, the technology demonstration transmitted a cumulative 13.6 terabits of data before concluding, by design, on September 2, 2025, having exceeded every technical goal the team set for it, and demonstrated data rates at least 10 times higher than a radio system of comparable size and power could achieve. A result that doesn't change anything about Psyche's own asteroid science, but that mission planners expect to directly shape how future spacecraft, potentially including crewed missions, communicate across deep space. In May 2026, Psyche successfully executed a gravity-assist flyby of Mars, passing within roughly 4,500 kilometers of the Martian surface, using the planet's gravity to bend its trajectory and adjust its orbital tilt so that its path aligns properly with the orbital plane of the asteroid Psyche itself. A necessary correction, since the asteroid's orbit is tilted several degrees relative to the plane most planets and asteroids roughly share. With that maneuver complete, the spacecraft remains on course for arrival at the asteroid in mid to late 2029, when Psyche's own weak gravity will capture the spacecraft into orbit, followed by roughly 2 years of close-range mapping, spectroscopy, and magnetic field measurement aimed at finally testing, directly, whether this strange metallic world really is what decades of remote observation have suggested it might be. Part 8: The Heartbeat of Mars. While spacecraft have been flying past asteroids and diving through the sun's corona, a very different kind of instrument spent 4 years sitting motionless on the surface of Mars, doing something no previous Mars mission had ever managed: listening. NASA's InSight lander touched down on Mars in November 2018 in a flat, relatively featureless plain called Elysium Planitia, chosen specifically for its lack of interesting surface geology. Because, unlike every rover mission before or since, InSight wasn't there to study the surface at all. It was there to study what's underneath it, using a suite of instruments built around a single central goal: understanding the deep interior structure of Mars, something no orbiter, rover, or telescope could ever accomplish, because that requires physically detecting and measuring vibrations traveling through the planet's interior itself. Not every instrument InSight carried worked as planned, and that failure is worth including here precisely, because this program has been honest about the successes. Alongside the seismometer, InSight also carried a self-hammering heat probe nicknamed the Mole, designed to burrow up to 5 meters beneath the surface, dragging a sensor cable behind it to measure how heat flows outward from Mars's interior. A measurement that would have complemented the seismic data with direct information about the planet's internal temperature. The Mole depended on friction from the surrounding regolith to brace itself with each hammer stroke, the same way a nail needs surrounding wood to grip against as it's driven in. Unlike Curiosity and Perseverance's landing sites, though, the soil beneath InSight turned out to be unexpectedly cohesive, clumping together instead of collapsing in around the Mole as it dug. So the probe kept bouncing in place without ever gaining the grip it needed to advance. Engineers spent nearly 2 years attempting workarounds, including using the lander's robotic arm and scoop to press down on the soil and pin the Mole from outside, before formally ending the effort in January 2021 and redirecting the arm and remaining mission resources towards supporting SCIS instead. It's a useful reminder that even a mission generally regarded as a clear scientific success carries a real instrument failure inside it, and that NASA's public reporting on InSight has never tried to hide that fact. The centerpiece instrument was a seismometer called SEIS, Seismic Experiment for Interior Structure, built with a sensitivity that's difficult to overstate. It was designed to detect ground motion on the scale of the width of a hydrogen atom, deployed directly onto the Martian surface by InSight's robotic arm, and covered with a domed thermal and wind shield to protect its extraordinarily delicate readings from Mars's own thin atmosphere and temperature swings, both of which can otherwise register as false seismic noise. Over its 4-year operational life, SCIS detected more than 1,300 Marsquarks, ranging from tiny, barely detectable tremors to a handful of substantial events, including the largest ever recorded on Mars, magnitude 4.7, detected in 2022. Mars doesn't have plate tectonics the way Earth does. There's no grinding of continental plates against each other. So Martian seismic activity instead comes primarily from the slow cooling and contraction of the planet's interior over billions of years, along with occasional meteoroid impacts strong enough to generate detectable seismic waves that ripple through the planet's interior. That second source, meteoroid impacts, turned out to matter more than expected. By cross-referencing seismic detections against orbital imagery that could spot fresh impact craters from space, scientists confirmed that meteoroid strikes generate seismic signals capable of reaching considerably deeper into the planet than earlier models predicted, giving researchers an unplanned but genuinely useful additional tool for probing Mars's interior structure using naturally occurring impacts as, essentially, free seismic sources scattered randomly around the planet. The way seismology reveals a planet's interior is conceptually elegant even though the underlying physics is intricate. When a Marsquark occurs, it sends 2 main types of waves rippling outward through the planet: faster-moving compressional waves and slower shear waves. And those waves travel at different speeds and bend, reflect, or get absorbed differently depending on the density, temperature, and physical state, solid versus molten, of the material they pass through. By precisely timing when different wave types arrive at a single seismometer, and by studying waves that reflect off internal boundaries deep inside the planet before returning to the surface, scientists can reconstruct a cross-section of a planet's interior without ever physically reaching it. Essentially, the same technique geologists use to map Earth's own core, mantle, and crust, using seismic waves generated by earthquakes. Applying that technique to Mars produced, over InSight's mission, 3 landmark findings. First, the Martian core. Seismic reflections bouncing off the core mantle boundary allowed scientists to determine that Mars possesses a molten, liquid metal core with a radius of roughly 1,830 kilometers, give or take about 40 kilometers. A core considerably larger relative to the planet's overall size than earlier models had generally predicted, and one whose measured density turned out to be lower than a pure iron-nickel composition would produce, implying the core must contain a substantial fraction of lighter elements, likely including sulfur, dissolved within the metal, alloyed in during the planet's earliest, hottest period of formation. Second, the mantle. Seismic waves traveling to depths of roughly 800 kilometers before returning to the surface revealed that Mars's outer rigid shell, the lithosphere, extends to a thickness of around 500 kilometers, remarkably thick compared to Earth's own lithosphere, consistent with a planet that has been cooling and stiffening, uninterrupted by plate tectonics, for billions of years. Third, the crust directly beneath the InSight landing site turned out to be thinner than pre-landing models had generally predicted, somewhere between 25 and 40 kilometers thick, and structured in 3 distinct sublayers. A layered structure broadly similar in principle, though certainly not in detail, to the layered crust geologists have long mapped on Earth. InSight's mission formally ended in December 2022, after its solar panels, gradually caked with wind-blown Martian dust that Mars's thin atmosphere and infrequent, gentle winds were never quite strong enough to reliably clear, could no longer generate sufficient power to keep the lander's systems and instruments running. But the seismic dataset it left behind is still very much an active area of research years later, with scientists continuing to publish increasingly refined models of Mars's interior structure, and open questions still very much unresolved, including exactly how much of Mars's ancient magnetic field, now entirely gone, might be connected to the behavior of that molten core over the planet's geological history, and why Mars, unlike Earth, apparently never developed the kind of ongoing plate tectonic activity that continuously recycles a planet's crust. One of those continuing threads of research concerns a specific stretch of terrain called Cerberus Fossae, a system of long, parallel fissures cutting across Elysium Planitia, not far from InSight's own landing site, and already suspected, well before InSight arrived, of being geologically younger than most of the surrounding plain. Cataloging InSight's full set of detected Mars quarks revealed that a striking share of the planet's total seismic activity, accounting for close to half of all the seismic energy InSight measured over its entire mission, originated from this one relatively narrow band of fractures, far more than its size would suggest if Martian seismicity were spread evenly across the planet. Closer analysis of the deepest, lowest frequency quakes traced back to Cerberus Fossae turned up a spectral signature consistent with a structurally weak, unusually warm source region roughly 30 to 50 kilometers down, the kind of signal seismologists on Earth would associate with a body of magma sitting relatively close to the surface, rather than purely with cold rock grinding along old fracture lines. If that interpretation holds up under continued analysis, it would suggest Cerberus Fossae isn't simply an ancient scar left over from Mars's geologically active past, but a location where magma may still be moving, slowly, beneath the surface today. A genuinely surprising possibility for a planet, long assumed to have gone volcanically quiet hundreds of millions, if not billions of years ago, and one that would mean the thick, cooling lithosphere in sight measured elsewhere on the planet isn't the whole story everywhere at once. Part 9, the longest conversation ever held. Now for two spacecraft that are, by a wide margin, the oldest and most distant human-built objects still operating, and whose most recent findings have genuinely surprised the scientists who have spent entire careers studying the data they send back. Voyager 1 and Voyager 2 launched in 1977, originally designed for a primary mission lasting roughly 4 years, built to take advantage of a rare alignment of the outer planets that occurs only once every 175 years, allowing a single spacecraft trajectory to use each planet's gravity to slingshot on toward the next. Voyager 2 flew past Jupiter, Saturn, Uranus, and Neptune in sequence, remaining to this day the only spacecraft to have ever visited either ice giant up close. Voyager 1 flew past Jupiter and Saturn, then used Saturn's gravity to bend its trajectory sharply upward, out of the plane most planets orbit within, sacrificing any chance at further planetary flybys in exchange for a close pass by Saturn's large moon Titan. Long before either spacecraft reached true interstellar space, each first had to cross an inner boundary called the termination shock, the point where the outward-flowing solar wind, which has been moving supersonically the entire way from the Sun, abruptly slows to subsonic speed as it starts to push up against the thin interstellar material beyond it, roughly the solar system's equivalent of a sonic boom, except standing still in space rather than trailing behind a moving aircraft. Voyager 1 crossed that inner boundary in December 2004, at a distance of about 94 astronomical units from the Sun. Voyager 2, on its more southerly trajectory, crossed its own termination shock in August 2007, at a somewhat closer distance, providing the first direct evidence that the shock's shape isn't a perfect sphere centered on the Sun. Between the termination shock and the heliopause lies the heliosheath, a vast, turbulent transitional zone where the slowed solar wind continues piling up against the interstellar medium for billions of additional miles, meaning both spacecraft spent the better part of a decade traveling through that intermediate zone before either one actually reached the interstellar boundary proper. Both spacecraft, their primary planetary missions long since complete, kept flying outward, and both eventually crossed a boundary that had never been directly measured before. The heliopause, the outer edge of the heliosphere, the vast bubble of solar wind and magnetic field the Sun blows outward through space, beyond which the thin, extremely diffuse gas and magnetic field of true interstellar space, the material between star systems, begins. Voyager 1 crossed that boundary in August 2012, becoming the first human-built object to leave the heliosphere entirely. Voyager 2, on a different trajectory, followed in November 2018. Both determinations were made using a mix of instruments, most importantly a sharp, sustained increase in the density of charged particles detected once each spacecraft crossed over interstellar space, despite being colder and far less energetic overall than the space nearer the Sun, turns out to be considerably denser in charged particles than the solar wind had become by that distance. A counterintuitive but well-confirmed result from both spacecraft independently. What's happened since has kept surprising the scientists monitoring the data. Voyager 1's plasma wave system, an instrument that doesn't measure particles directly so much as detect the natural oscillation frequency of the surrounding plasma, the ionized gas the spacecraft is moving through, which allows scientists to calculate the plasma's density, even when the density is far too low for direct particle counters to register reliably, picked up a continuous, persistent hum of plasma wave activity once the spacecraft was well into interstellar space. A low, steady signal rather than the occasional sharp bursts associated with solar events, suggesting interstellar plasma has more structure and ongoing low-level activity than the largely empty, quiet void many scientists had expected to find out there. Perhaps the more striking result involves temperature. Data gathered from both spacecraft's plasma instruments after crossing the heliopause indicated that the material immediately beyond the boundary, technically, the very inner edge of the interstellar medium, in the transitional region still shaped by the heliosphere's interaction with the material around it, carries an extremely high electron temperature, with estimates in the range of 30,000 to 50,000 Kelvin, dramatically hotter than the roughly 10,000 degree Fahrenheit surface of the Sun itself when converted to comparable units. That sounds contradictory on its face. How can it be simultaneously true that interstellar space is popularly described as bitterly cold, and that the Voyagers measured plasma temperatures in the tens of thousands of degrees? The resolution lies in the extraordinarily low density of that plasma. Temperature in physics technically describes the average kinetic energy of individual particles, not the total heat-carrying capacity of a material. And interstellar plasma is so sparse, with particles spread so far apart, that despite each individual particle moving at very high energy, there are nowhere near enough particles packed into any given volume to transfer that energy efficiently the way a dense gas or solid would. The Voyager spacecraft themselves are in no thermal danger from this hot wall, because there's essentially nothing there to conduct that heat into the spacecraft's own structure. But the finding itself remains a genuine puzzle for the physics of the outer heliosphere boundary, an area of ongoing modeling and debate within the heliophysics community, since it's not fully explained by pre-Voyager models of how the heliosphere should interact with the surrounding interstellar medium. Separately, magnetic field measurements from both spacecraft turned up another result that ran against expectations. The direction of the magnetic field lines just outside the heliopause, in true interstellar space, turned out to align remarkably closely with the direction of the magnetic field lines just inside it, within the heliosphere. A surprising continuity, since many earlier models had predicted a more substantial directional shift at the boundary, given that the two magnetic field systems originate from entirely different sources, one from the Sun and one from the broader galactic environment. Staying in touch with either spacecraft across that kind of distance has never been a given, and two recent incidents make clear just how thin the margin actually is. In July 2023, a routine set of commands sent to Voyager 2 inadvertently pointed its main antenna about 2 degrees away from Earth. A tiny error by any ordinary standard, but more than enough, at a distance of roughly 12.3 billion miles, to break the narrow radio link entirely, leaving the spacecraft unable to receive commands or send data home. Rather than wait roughly 7 months for Voyager 2's own onboard programming to automatically reorient itself, as it's designed to do periodically as a safeguard, engineers at NASA's Deep Space Network used an extremely high-power transmission from the Canberra, Australia tracking facility, informally described at the time as an interstellar shout, to send a single corrective command across that entire distance. With a one-way radio delay of about 18.5 hours each way, the team had to wait roughly 37 hours to find out whether the command had worked before Voyager 2 resumed sending data on August 4, 2023. Voyager 1 had its own scare the following year. On October 16, 2024, a routine command intended to adjust a heater unexpectedly triggered the spacecraft's autonomous fault protection system, which responded by cutting power to the primary X-band transmitter and switching over to a backup S-band transmitter that hadn't been used since 1981, more than 4 decades of sitting dormant. The backup transmitter uses a fundamentally weaker signal. Engineers weren't certain the Deep Space Network could even reliably detect at Voyager 1's distance, but it worked well enough for controllers to diagnose the fault and carefully, deliberately, work the spacecraft back onto its primary transmitter, restoring the normal daily stream of science and telemetry data by mid-November 2024. Both incidents ended the way engineers wanted them to. Both are also a reminder that every single piece of data in this section of the program is arriving via hardware older than most of the people who currently operate it, running on procedures and backup systems that were designed, and then not needed, decades before anyone knew they might someday matter again. Both spacecraft are unavoidably running down. They're radioisotope thermoelectric generators, power sources that convert the heat from the natural radioactive decay of plutonium-238 into electricity, since sunlight at that distance is far too faint for solar panels to be useful. Lose a small, steady, unrecoverable fraction of their output every year. And mission engineers have spent the last decade methodically switching off one instrument after another on each spacecraft to conserve the dwindling power that remains for the instruments still considered highest priority. Voyager 1 experienced a series of unexpected but successfully resolved thruster and computer issues in recent years, including a notable communications glitch in 2023 that briefly left the spacecraft sending back unreadable data before engineers, working across a round-trip radio delay of roughly 45 hours given the spacecraft's distance, diagnosed and corrected a corrupted memory chip through a remote software patch. Current projections suggest both Voyagers will likely lose the ability to power any remaining scientific instruments sometime around the end of this decade, at which point both spacecraft will continue coasting outward silently, carrying their golden records for essentially the rest of time, long after they've stopped talking to us. Each of those records is a gold-plated copper phonograph disc, bolted to the outside of its spacecraft along with a cartridge, needle, and pictorial instructions for playing it, carrying 116 images encoded as analog data, greetings recorded in 55 different human languages plus one from a humpback whale, a broad survey of Earth's natural sounds, and roughly 90 minutes of curated music spanning cultures and centuries. Assembled by a committee that included astronomer Carl Sagan and was tasked with representing humanity to whoever, if anyone, might ever recover it. No one involved in assembling it expected it to be found any time soon. The nearest star system either spacecraft will pass anywhere close to is still tens of thousands of years away at their current speed. But its presence on both spacecraft was, and remains, a deliberate statement that these missions were never framed purely as engineering exercises. They were built, from the very beginning, to carry something worth saying, on the chance that saying it ever actually mattered to someone other than us. For now, they're still talking, and what they're still saying continues to complicate the tidy picture of interstellar space that existed before they got there. Part 10, The Frozen Library at the Edge. Voyager and New Horizons, which we'll get to in a moment, aren't the only NASA-connected efforts working the far edge of the solar system. Webb has been doing its own version of that work without ever leaving Earth's orbital neighborhood, by turning its infrared instruments on the population of icy dwarf planets and smaller bodies scattered through the Kuiper Belt, the vast ring of leftover material beyond Neptune's orbit that never finished forming into planets. In observations released in stages through 2024 and early 2025, an international research team used Webb's NIRS-SPEC instrument to study 3 of the larger known Kuiper Belt objects, the dwarf planets Sedna, Gonggong, and Quaoar, gathering infrared spectra detailed enough to identify specific ices frozen onto their surfaces. All 3 showed a clear signature of ethane ice, a hydrocarbon compound that forms through the slow radiation processing of methane over billions of years of exposure to cosmic rays and ultraviolet light in the cold, dark outer solar system. Sedna's spectrum went further, revealing additional light hydrocarbons, ethylene and acetylene, an even more chemically processed mixture consistent with Sedna's position as one of the most distant and coldest large bodies ever studied in the solar system, looping out on an orbit that carries it, at its farthest point, hundreds of times farther from the Sun than Earth ever gets. A separate part of the same broader observing program, run through the University of Central Florida, has been surveying a wider sample of trans-Neptunian objects specifically to map where methanol ice shows up across the population. Methanol being another carbon-bearing building block molecule relevant to the same kind of prebiotic chemistry OSIRIS-REx found locked inside Bennu, just observed here from a completely different distance and through a completely different method. Spectroscopy rather than sample return. Taken together, the Surface Chemistry Survey has let researchers sort Kuiper Belt objects into distinct spectral categories that team members have taken to calling, somewhat informally, bowl types, double dips, and cliffs, categories that appear to trace back to how close to the Sun each object's building blocks originally formed. Material that formed nearer the Sun's early heat had more of its carbon dioxide and methane baked off before it ever got cold enough to freeze permanently in place, while material that formed farther out, in the coldest fringes of the primordial disk, held onto those same volatile ices far more completely. None of this is only about the Kuiper Belt in isolation. Because Neptune is thought to have migrated substantially outward from where it originally formed, dragging some of these icy bodies along with it or scattering others into their current wide, eccentric orbits along the way, mapping the chemical differences across today's Kuiper Belt population gives researchers indirect evidence about where in the early disk different objects actually condensed, before Neptune's migration ever rearranged them. Evidence that feeds directly into the same broader story the rest of this program keeps circling back to, figuring out what raw material was available where, and how much of it eventually ended up incorporated into the planets we actually live among today, versus scattered and frozen at the edge of everything, waiting for an infrared telescope a million miles from Earth to finally read its composition properly for the first time. Part 11. The Visitor from Another Star. Every object covered so far in this program, no matter how strange, has belonged to our solar system, formed from the same original disk of gas and dust that built the Sun and everything orbiting it. In July 2025, NASA and the wider astronomical community got a chance to study something that didn't. An object called 3I Atlas, first spotted on July 1, 2025, by the Atlas Survey Telescope Network, a system of automated telescopes built primarily to hunt for asteroids on a collision course with Earth, which turned out, in this case, to have caught something that had never been anywhere near Earth before at all. The 3I in its name marks it as only the third interstellar object ever confirmed passing through the solar system, following Oumuamua in 2017 and Borisov in 2019, meaning that in the entire history of astronomy, humans have now directly detected exactly 3 objects that formed around other stars and happened to drift close enough to our own for telescopes to catch. The first 2 set up very different expectations for what a fourth might look like. Oumuamua, spotted in October 2017, was small, faint, and gone from view within weeks, showing no coma or tail at all, and displaying an unusual rapid tumble and an odd, unexplained extra push away from the Sun that fueled years of competing explanations, from unusually shaped nitrogen ice to simple outgassing too faint for period telescopes to directly detect. Borisov, found in 2019, behaved far more like an ordinary solar system comet, complete with a visible coma and tail, but its gas was unusually rich in carbon monoxide relative to water, another sign that its parent star's disk cooked up ices in different proportions than our own did. Unlike Oumuamua, which showed no visible coma or tail and left scientists arguing for years about its exact nature, 3I Atlas quickly proved to be an active comet, venting gas and dust as sunlight warmed its surface during its passage through the inner solar system, making it only the second interstellar visitor, after Borisov, to display that kind of clear cometary activity. and the first one bright and active enough for an instrument as sensitive as Webb to get a detailed look at its actual chemistry, rather than just its trajectory. That look came on August 6, 2025, when Webb's NIRS-SPEC instrument captured an infrared spectrum of 3I Atlas, while the object was still about 3.32 astronomical units from the Sun, roughly 3 1/3 times the Earth-Sun distance, comfortably out past Mars's orbit. The spectrum showed a coma, the cloud of gas and dust surrounding the object's icy core, dominated overwhelmingly by carbon dioxide, alongside water, carbon monoxide, water ice, dust, and a tentative, not yet fully confirmed detection of a sulfur-bearing compound called carbonyl sulfide. The carbon dioxide to water ratio measured out at roughly 7.6 to 1, among the highest such ratios ever recorded in any comet, solar system, or interstellar, and measured at a level statistically far enough outside the normal trend line for comets at that distance from the Sun that researchers are confident it reflects something genuinely unusual about where and how 3I Atlas originally formed, rather than any error in the measurement itself. Scientists studying the result have floated a couple of competing explanations, and true to the careful pattern that's run through this entire program, haven't yet settled on which one is correct. One possibility is that 3I Atlas spent a very long time, potentially billions of years, traveling through interstellar space before reaching us, absorbing a higher cumulative dose of cosmic radiation than a typical solar system comet ever experiences, which can alter surface ice chemistry in ways that might produce an unusually CO2-rich coma once the object finally warms up near a star. The other possibility is more fundamental, that 3I Atlas simply formed around whatever star it originally belonged to, in a region of its birth disk cold enough for carbon dioxide ice to freeze out and dominate the local ice budget from the very beginning, in a way that's less common closer to a typical star, including our own. Either explanation would mean the same broader thing, that the building blocks available around other stars aren't identical to the ones that built our own solar system, and that objects like 3I Atlas are, for however brief a window they're passing through, the only direct physical samples of that other chemistry astronomers currently have any way to study at all. Because 3I Atlas is moving on a hyperbolic trajectory, meaning it's not gravitationally bound to the Sun and will never return, unlike a typical solar system comet on a long elliptical orbit, the observing window was always going to be brief. Every instrument that could be pointed at it during its short passage through the inner solar system, Webb included, was working against a hard deadline that no amount of additional funding or mission planning could extend. That urgency is part of why an interstellar visitor like this one generates such a fast, compressed burst of research activity compared to a planned mission like Europa Clipper or Psyche. There's no waiting for a better launch window or a longer cruise phase. There's only the object, passing through once, and however many telescopes on Earth and in space happen to be ready to look at the moment it arrives. Part 12, The Other Explorer at the Edge. Voyager 1 and Voyager 2 aren't the only NASA spacecraft working the transition zone between the solar system and true interstellar space, even if they're the only ones that have actually crossed all the way into it. New Horizons, the mission best known for its 2015 flyby of Pluto, which returned the first close-up images of that dwarf planet, and its moons after a 9.5-year journey across the solar system, has spent the years since operating in an extended phase specifically built around studying the Kuiper Belt and the outer edge of the heliosphere from a vantage point Voyager never had the instruments, or the mission design, to fully exploit. That 2015 flyby is worth a moment of its own credit, because it reshaped how scientists think about small, cold worlds generally. Pluto turned out to have a surprisingly active surface for a body so far from the Sun's warmth, including a smooth, nitrogenized plain nicknamed Sputnik Planitia, mountain ranges made of water ice strong enough to hold their shape at Pluto's frigid temperatures, and evidence of a subsurface ocean of its own, kept liquid, much like Europa's, by a combination of radioactive decay and gravitational effects, this time from Pluto's proportionally enormous moon Charon rather than a nearby giant planet. That single flyby, packed into a matter of hours as New Horizons streaked past at roughly 30,000 miles per hour, produced more data about Pluto than the sum total of everything telescopes had managed to determine about it since its discovery in 1930. After Pluto, New Horizons went on to fly past a small, distant Kuiper Belt object called Arrokoth on January 1, 2019. Still the most distant object any spacecraft has ever examined up close, a contact binary shaped like two flattened lobes gently stuck together, offering a rare, well-preserved look at the kind of small, cold building block that Kuiper Belt formation models predict should be common out there, but that almost nothing has ever actually visited directly. Since then, the mission has been operating under what NASA calls its second Kuiper Belt extended mission, a phase approved to carry New Horizons through the region of space between roughly 54 and 75 astronomical units from the Sun, considerably farther out than Pluto's own orbit, though still, notably, well short of where either Voyager crossed the heliopause into interstellar space. New Horizons carries 7 science instruments, including a compact energetic particle spectrometer called PEPSSI, described by the mission team as the smallest, lowest power instrument of its kind ever flown, along with a dedicated dust counter and plasma sensors built to measure the solar wind's charged particle environment as it thins out with distance from the Sun. Running continuously, those instruments are gathering exactly the kind of heliosphere and interplanetary dust data that complements what Voyager 1 and Voyager 2 measured decades earlier at a very different, more distant boundary, giving researchers a second, independent vantage point on how the heliosphere's structure changes across tens of billions of miles, gathered by an actively operating, fully instrumented spacecraft, rather than by 2 aging probes running an ever-shrinking subset of their original hardware. In August 2025, mission managers put New Horizons into its longest hibernation period yet, a deliberate power and cost-saving measure that dims most of the spacecraft's systems for extended stretches between active observing campaigns, preserving its remaining resources for a cruise that mission planners expect could continue for years, or potentially decades, if a suitable next Kuiper Belt object worth a dedicated flyby turns up along its path. A targets of opportunity approach that means, much like Lucy waiting on its first real Trojan encounter, some of New Horizons' most interesting science may still be ahead of it rather than behind it. Part 13. More Eyes on Old Worlds. Before we pull all of this together, it's worth acknowledging a handful of additional findings that don't each carry an entire chapter's worth of mission history, but that round out just how broadly Webb, in particular, has been rewriting entries across the solar system over the past few years. At Jupiter's volcanically violent inner moon Io, the most volcanically active body known anywhere in the solar system, its surface constantly resurfaced by hundreds of active volcanoes driven by the same kind of tidal flexing that keeps Europa's ocean liquid, only far more intensely, since Io sits closer to Jupiter and experiences correspondingly stronger tidal stress. Webb's infrared instruments observed an extremely energetic eruption near a lava field called Cainhically Fluctus and detected, for the first time, an excited form of sulfur monoxide gas being emitted from an Io volcano, directly confirming a hypothesis about Io's volcanic gas chemistry that had been proposed on theoretical grounds roughly 2 decades earlier, but never directly observed. In the same set of observations, Webb detected neutral sulfur atoms in Io's thin atmosphere for the first time, and picked up an increase in thermal emissions from Loki Patera, one of Io's largest and most persistent lava lakes, a signal consistent with periodic overturning of the lake's solidified crust, where the thick, cooling surface skin of the lava lake episodically breaks apart and sinks back into the molten material beneath it, exposing fresh, hotter lava and producing a corresponding brightness surge. At Saturn's largest moon, Titan, a genuinely strange world in its own right, the only moon in the solar system with a substantial atmosphere, thick enough that its surface pressure actually exceeds Earth's, and cold enough that instead of liquid water, Titan has lakes and seas of liquid methane and ethane pooled across its northern polar region. A research team combined Webb observations with ground-based data from the Keck Observatory in Hawaii to observe direct evidence of atmospheric cloud convection above Titan's northern hemisphere for the first time, in the same region where most of Titan's lakes are concentrated, a process believed to be connected to the occasional methane and ethane rainfall that periodically replenishes those lakes. The same observing campaign also detected a specific carbon-containing molecule in Titan's atmosphere that offers a new data point for understanding the complex chain of photochemical reactions occurring in that atmosphere's hazy upper layers, reactions that produce much of the orange-brown organic haze that gives Titan its distinctive, smog-like appearance from space. Saturn itself, not just its moons, has come in for renewed attention too. Webb's first near-infrared look at Saturn, taken in June 2023, produced an oddly inverted image compared to what casual observers might expect. The planet's disk appeared almost completely dark, because methane gas in Saturn's atmosphere absorbs nearly all the sunlight at the wavelengths Webb was observing, while the icy rings, made of far more reflective material, stayed comparatively bright, leaving Saturn looking, in that image, like a faint, ghostly ball wrapped in a glowing halo. Separate mid-infrared spectroscopy, mapping Saturn's northern hemisphere as it moved deeper into its own decades-long summer season, found stratospheric temperatures and chemical patterns that didn't fully match what Cassini had recorded at the equivalent point in Saturn's previous seasonal cycle, back during its northern winter and spring. A reminder that even a planet as thoroughly studied as Saturn, host to one of the longest and most productive orbital missions NASA has ever flown, still has atmospheric behavior that doesn't repeat identically from one 29-year orbit to the next. And even Mars, the most visited and photographed planet in the solar system after Earth, wasn't left out. Webb captured its first infrared images and spectra of Mars in September 2022, and despite Mars being one of the most extensively studied objects in the solar system, Webb's particular observational capabilities, infrared wavelengths, and a level of spectral sensitivity not available from Mars orbiters designed for other purposes, allowed researchers to study the Martian atmosphere's composition and dynamics from an entirely different vantage point than the surface-level and orbital instruments already there, adding another data source to the long-running effort to understand Mars's atmospheric chemistry and its slow, ongoing loss of atmosphere to space over geological time. None of these individually rewrites a textbook chapter on its own, but taken together with everything else in this program, they illustrate something that's easy to lose sight of if you only pay attention to the biggest single headlines. This hasn't been one telescope making one big discovery, or one spacecraft having one dramatic moment. It's been a genuinely broad, sustained, overlapping campaign, running across nearly every category of object in the solar system simultaneously for the better part of a decade. Part 14, What It Adds Up To. Step back now and look at everything we've covered together, because the individual results are only half the story. The other half is the pattern they form when you line them up side by side. An asteroid, Bennu, carrying the raw chemical building blocks of biology and mineral evidence of ancient liquid water, sustained inside a rock for an extended stretch of time, sampled with a spacecraft precise enough to touch down for 6 seconds and grab material from 200 million miles away. An ice-crusted moon, Europa, apparently venting its own subsurface ocean chemistry onto its surface, where an infrared telescope parked a million miles from Earth could detect it, with a dedicated spacecraft now in transit to go find out what that chemistry actually means. Another ocean moon, Enceladus, doing something similar but more directly, spraying a plume of its own interior water hundreds of thousands of miles into space, sampled in astonishing detail from Earth orbit. Two ice giants, Uranus and Neptune, visited exactly once each, decades ago, now being re-examined by an infrared telescope revealing rings, storms, and temperature shifts nobody had a clear picture of before. Our star, finally being flown into directly, its outermost atmosphere sampled in place by a heat shield-protected spacecraft, moving faster than any object humans have built. A cluster of ancient asteroids sharing Jupiter's orbit, understood as a scattered library of material from across the early solar system, now being visited one by a spacecraft with a flight plan more ambitious than anything attempted before it. A metal-rich asteroid that might be the exposed core of a shattered protoplanet, being approached right now by a spacecraft that survived its own propulsion crisis along the way. A planet, Mars, that let us listen to its own interior for the first time through a seismometer sensitive enough to hear a hydrogen atom's width of motion. And two spacecraft older than most people alive today, still transmitting from beyond the edge of the sun's influence, describing a boundary between our solar system and true interstellar space that keeps turning out to be hotter, stranger, and more structured than the models predicted. And that's before counting everything this program has covered beyond that first list. A frozen library of dwarf planets and smaller bodies scattered through the Kuiper Belt, their surface ices now being read one infrared spectrum at a time, tracing back to exactly where in the early solar system's disk each one actually formed. A visitor from another star entirely, the third interstellar object ever confirmed, and the first bright enough for Webb to read its chemistry in detail during the few short months it was ever going to be close enough to look at. A second spacecraft, New Horizons, still working the outer edge of the heliosphere from a vantage point closer than Voyager's, still gathering data on the same boundary from a different angle. An experimental laser link, riding along on Psyche's hardware, that spent 2 years proving deep space communication doesn't have to stay tied to radio forever. And two fully designed, ranked, and waiting flagship mission concepts, one for Uranus, one for Enceladus, sitting on the shelf, engineering studies complete, waiting only on funding and a launch date to turn everything this program has described as still hypothetical into the next round of direct, close-up evidence. None of these, individually or collectively, are announcements that we've found life, or finished mapping the outer solar system, or solved solar physics, or fully understood a single planetary interior. Scientists working on every one of these missions have been consistently, deliberately careful about that distinction, and that carefulness is not a limitation of the science. It's the discipline that makes the science trustworthy in the first place. Every finding in this program went through some version of the same process. An initial detection, often surprising and sometimes contradicting what the team expected going in. Independent replication or cross-checking, frequently using different instruments or different laboratories. Peer review, where outside experts with no stake in the original result get to challenge the methodology and the conclusions before anything is formally published. And then, often, years of continued follow-up work refining, qualifying, or occasionally revising the original finding as more data comes in. That's slower and less dramatic than a single triumphant headline. It's also the only process that's actually earned the right to be trusted. What connects everything in this program isn't a single discovery. It's a pattern of narrowing gaps between not knowing and knowing, between suspecting something might be true and having direct evidence that it is. Bennu's archived sample material is still being analyzed, with new papers expected for years. Europa Clipper is still years from arrival, carrying instruments built specifically to test what Webb's chemistry hinted at. Lucy's real encounters with the Trojan swarm haven't even started yet. Psyche is still 4 years from reaching the world it was built to study. Parker's solar probe continues its extended mission, still diving through the corona on a repeating schedule. And Voyager 1 and Voyager 2, however many working instruments they have left, are still out there, still describing a region of space no other human-built object has ever reached, for as long as their dwindling power allows them to keep talking. The solar system we thought we'd already mapped, growing up looking at diagrams in textbooks, 8 planets, a scattering of moons, an asteroid belt, done keeps turning out to have more open questions in it than closed ones, the deeper any single mission actually looks. That's not a failure of earlier science. It's what happens when instruments get better, when spacecraft get bold enough to fly closer, land longer, listen harder, and sample more precisely than the missions before them ever could. The answers aren't finished. They're arriving in pieces, sample by sample, flyby by flyby, seismic wave by seismic wave, image by image. And if you're the kind of person who finds a finished, settled answer less interesting than an active, ongoing investigation, then this is, honestly, the best possible way to be watching it happen. In real time, with the uncertainty still showing, with entire missions still in transit toward encounters nobody has had yet. If a program like this one is doing its job, it was never going to end by telling you the mystery is solved. Its job was always to tell you where the working, funded, currently flying evidence says to look next, and after everything we've just walked through, that list is longer, not shorter, than it was when we started.